Glad to see everybody here today. We've got a big dinosaur exhibit here this summer. Man, I used to love dinosaurs as a kid. I mean, I still kind of do. Yeah, space is really my focus now. I got to see the Tyrannosaurs Meet the Family exhibit on Monday. Pretty impressive. I hope all of you get to come see it this summer as well. Definitely worth it. But in case you hadn't noticed, the dinosaurs are gone now, at least most of them. And the ones that do remain here on the Earth, mere shadows of their former selves. So I think it's worth talking about why the dinosaurs are no longer with us, or perhaps why we are here at all. That requires a little bit larger focus, a little bit wider view. We're going to be looking across the solar system and focusing on some of the smallest members of the solar system. This talk is really an extended version of my ongoing planetarium series, Better Know an Asteroid, or It Came from Outer Space, what the dinosaurs didn't know, and I've added, since we started advertising the talk, why we better know. It's also good timing for this topic because 1 week from today, June 30th, is Asteroid Day. That is a UN-sanctioned day of awareness all about asteroids and the threat they pose to the Earth. One thing I don't want to do in today's talk, though, is overstate the risks. So let's start by laying a foundation with some terms and numbers that it might be helpful to keep in mind during today's presentation. Let's start with the biggest number, 1.1 million. That is the number, approximately, of minor planets that astronomers have identified in the solar system. Now, for an astronomer, a minor planet is anything smaller than a dwarf planet that could be all the way out beyond Neptune. So when we talk about asteroids, we're usually focused on those that are inside the orbit of Jupiter. That's most of that 1.1 million. Now, within the 1.1 million or so asteroids, there are near-Earth asteroids. As that name suggests, these are the asteroids that come kind of close to the Earth. They have to get within 1.3 astronomical units of the sun, 1 astronomical unit being the Earth's distance from our star. Then, within those near-Earth asteroids, there are potentially hazardous asteroids. These get really close to the Earth, within 0.05 of an astronomical unit. That's about 19.5 times the moon's distance from the Earth. And they're fairly large, about 140 meters in diameter or larger. The populations of some of these asteroids, to give you an idea that the numbers are always changing, but as of last week, near-Earth asteroids, we were up over 26,000 of those, and the potentially hazardous asteroids numbered almost 2,200. A little over 2,000 potentially hazardous asteroids. But the most important number out of all of these is the number 0. We know of exactly 0 asteroids. They're actually on an impact course with the Earth. So we don't have any immediate impacts to worry about. Some get pretty close to us, though. And there are many others we haven't found yet. I don't think we're missing too many of the really big asteroids, the ones that could really cause worldwide destruction. Here is a little chart that shows how we're doing in terms of discovering asteroids. This is actually kind of old data. This is from 2011. So each picture of an asteroid here represents 100 asteroids of each size range that's numbered out there. So doing pretty good with the really big ones. It's easier to find big asteroids because they reflect more sunlight. We can see them from farther away. As we get farther down the list, we find fewer of them just because it's harder to spot. And I did say this was old data, so let's update this chart a little bit. Based on current numbers, well, we're actually doing pretty good with kind of the medium-sized asteroids as well, but we still have a lot to find on the smaller end of the spectrum. And in fact, some of those small ones can even sneak up on us. You don't have to be 140 meters wide if you're an asteroid to cause destruction here on the Earth. Asteroids as small as 20 meters in diameter are capable of wiping out a city. So we've got to watch out for the small ones too. And sometimes little tiny ones sneak up on us. It happened twice just last year. In late August, an asteroid, called 2020 QG right now, followed the orange line that I'll bring up on the bottom part of your screen here, flew right by the Earth. We didn't even see it until it had made its closest approach to the planet. That, at the time, was the record for the closest observed asteroid approach. Then a couple of months later, the record was broken. Another small asteroid, 2020 VT4, got even closer. That's the one leaving the red trail across your screen. VT4 passed just a few hundred kilometers above the surface of the Earth. That is a similar altitude to our low Earth orbit satellites. Now, both of these asteroids, luckily, if they had hit the Earth, just a few meters in diameter, so they more than likely would have burned up in the atmosphere, maybe exploded in the air, not likely to reach the surface and cause any damage at all. But if we didn't see these asteroids coming, it kind of makes you wonder how well we're really mapping out the solar system. How can we do a better job of keeping track of these asteroids? Well, their very existence and their very nature makes it difficult to keep an eye on them. Let's use the one with the red trail as an example here. You can see that the path of 2020 VT4 was altered by its flyby of the Earth. Let's get a little bit wider view here, and I'll show you its path around the sun. It would be one of those near-Earth asteroids. It came close enough to the sun to qualify in that group. And here is the orbit that it used to follow. So it went way out beyond the orbit of Mars, and it came in towards the orbit of the Earth. Now, after passing by Earth last November, it's on this new orbit, still crossing Earth's orbit, and now it looks like it approaches the orbit of Venus as well. So now it's got another planet whose gravitational influence may affect its trajectory in the future, and that kind of thing is going to make it a little bit more difficult to predict its future trajectory. We have the same kind of concern with all of these near-Earth asteroids, so it becomes quite a puzzle to keep track of all of them. So if there are larger ones out there and they are going to hit, how do we know they actually pose a danger? Well, the Earth bears the scars of many previous impacts. For those of us in central Virginia, we actually live pretty close to the site of a major impact that took place about 35.5 million years ago. Need to zoom back in and find the Chesapeake Bay here, so bear with me just a second as we fly in. All right, that's the Western Pacific. So we're going to circle around here. Now, the Chesapeake Bay Impact crater is, it's about 85 kilometers in diameter. That's about 53 miles. The asteroid that created it, we think, was about 3 kilometers or 1.9 miles wide. All right, there we are there. Now, when this asteroid struck, it would have caused regional destruction. It's pretty big, wide region would have been affected by the fallout from this impact. Would have caused a very large tsunami as well. This was 35.5 million years ago, so conditions on Earth were just a little bit different. I think ocean levels were a little bit higher. So let's update our map here. Richmond would have been either right on the coast or maybe underwater at this time. So is hitting shallow ocean water. The tsunami may have washed inland all the way to the Blue Ridge Mountains. So that's pretty dramatic already. Recent exploration of this underground crater using boreholes. They're drilled down into the ground. You pull up these core samples. Scientists analyzing those have found ancient seawater deposits buried deep underground inside the Chesapeake Bay crater. I think the salt water is about 100 million years old. So it's a pretty interesting find right next door to us here. That ancient seawater records conditions in the Cretaceous oceans, shows they were a little bit different from the oceans of today, a little bit higher salt levels, so that's interesting to learn. And the existence of this crater is still affecting the region today. Sediment is still slumping into the crater. It's actually causing the seafloor and some of the land around the bay to sink. The subsidence is actually exacerbating the effects of sea level rise. So it's something that we need to keep an eye on. So yeah, one impact crater close to us here, still a part of our lives. And there are many other craters spread around the world. Each yellow cross that I've got on the map here is the location of another known impact feature. There are also red circles on all of them. You may not be able to pick out very many of those red circles. Those are scaled to the size of the impact crater. This is only the biggest ones that are really showing up at this scale. Now, there are some regions where we don't see a lot of impact craters. Does that mean nothing has hit the Earth there? Well, no, not necessarily. There are some problems with finding impact craters here on the Earth. We've got wind erosion, water erosion, Earth's active geology erases those craters. And of course, we've got the oceans, where if something hits the ocean, it's not likely to leave a crater that we can actually find. So it becomes a bit of a challenge to piece together the impact history of our planet. Luckily, we've got a neighbor that keeps better records than we do, the moon. So let's head next door here. Now, geologists can travel all over the Earth and study impact craters here. We haven't sent many geologists to the moon to study those craters in person. We've mapped the moon in some detail, and the moon helps us out. It doesn't have an atmosphere, so there's no wind erosion here. And that also means that just the appearance of a crater helps us figure out its age. Over time, micrometeoroid impacts on the moon and thermal cycles over the lunar day break down rocks and turns big boulders into the fine, dusty regolith that covers the surface of the entire moon. So by counting how many big chunks of rock are in these craters, we can figure out kind of how old they are. It's a little bit like our attics or basements might be. The old things are covered in dust, the newer things not so much. A recent study of relatively young, less than 1 billion year old craters on the moon that were of modest size, about 10 kilometers or 6.2 miles wide, showed there's been a recent uptick in these large impacts on the moon, especially in the last 290 million years or so. Now we can expect the Earth to follow those same patterns. And indeed, some of the largest craters preserved on Earth are from this younger time frame. Chesapeake Bay, 35.5 million years, and the largest crater that we know of on Earth from that time period, the Chicxulub Impact. Chicxulub Impact is the one that has been linked to the extinction of the non-avian dinosaurs. It is centered off the Yucatan Peninsula in southeastern Mexico, so let's track it down here. It's a pretty big crater. It's about 150 kilometers or 93 miles in diameter. The impactor, although we don't know precisely how large it was, we can estimate is something in the neighborhood of 10 kilometers or 6.2 miles wide. It would have hit the Earth about 66 million years ago. Now, we're centered right over the location of this impact, but I don't see a crater. Luckily, just like the Chesapeake Bay impact has shaped some of our local geology and geography, this ancient impact has shaped some features of this region as well. Although we don't see the crater right away, there are some clues hiding more or less in plain sight. To get right down on the ground in the Yucatan Peninsula, you can't go too far without running into some characteristic features of the region. Humans have known about them for a very long time. There are sinkholes all across this part of the Earth called cenotes that the Maya civilization used as a water source and as ritual sites. They still draw tourists to the area today. You can go scuba diving in them, which is pretty cool. And there's a set of these cenotes that forms kind of a unique feature here. There's an arc that goes from one part of the coast to the other. I've filled out the arc here to make a ring. This feature is called the Ring of Cenotes, and we've known it was there for a really long time, but we didn't know why. Some more clues started to surface in the 1970s. Around 1978, some geologists working for a state-run oil company in Mexico were prospecting in the area, and they were mapping out gravitational anomalies. I've got a more recent example of this kind of data. Now, gravitational anomalies are caused when the underlying terrain varies from what we would expect from the Earth just being a uniform, homogeneous sphere of rock. So you might have a gravity anomaly because there's something less dense underground. It might be water, it could be the oil these geologists were hoping for, or you could have anomalies because there's something more dense underground, a different kind of rock, something like that. But in 1978, these concentric rings were identified. And that's kind of a fingerprint of a buried impact crater. So we've got some telltale signs in the rocks here that some kind of big impact happened. In fact, the impact may have fractured the limestone bedrock in this region, actually let the water in that formed the cenotes. So all of this could really be linked together. But we aren't just interested in what happened to the rocks in this region. This impact, if it did happen 66 million years ago, it could be tied to the Cretaceous-Paleogene boundary. That's something that we see in rocks all around the world, and there seems to have been a mass extinction at that time. Up to 75% of the species here on Earth were wiped off of the planet. All kinds of life forms were affected. We're talking microbes, marine animals, plants. I don't know, what's your favorite kind of animal? Turtles, some birds, some mammals, all kinds of life affected by this impact. Environments all over the planet. And of course, the group of animals that gets the most attention are the dinosaurs. The non-avian dinosaurs wiped out in this impact. At least we think this is what caused it. How do we know? We've got this crater, but how do we know that one impact could have such wide-ranging effects? Well, first, this one impact has left marks not just in the Yucatan, but all over the planet. The so-called Kpg, or Cretaceous-Paleogene boundary, can be found in rocks all over the Earth. It's been located in hundreds of sites. This is an example in Colorado. You see that dark band kind of right in the middle of the image. That's it. That is the record of this ancient impact. There are a couple of unique things about this layer in the rocks. In 1980, Walter and Luis Alvarez identified was come to be known as the iridium anomaly in this layer. It's found in the Kpg boundary all over the planet, a little bit higher in North and South America, a little bit lower elsewhere. Now, the rocks just below and above this layer, much lower in iridium. Some asteroids are pretty high in it. So the Alvarezes suggested that it could have been an asteroid impact that led to this iridium anomaly. There are other things found in this layer as well. Shocked quartz and tektites, those little glass beads that we know form in impacts. So a lot of hints that there was an impact large enough to spread debris all over the planet. And because of the iridium, we're pretty sure the rock came from outer space. Pretty sure it was an asteroid. Now, I don't have time to get into all of the details, all of the aftermath of this impact. So I'm going to take a quick water break, and please enjoy for the next few seconds some of the other things that this asteroid impact caused. All right, so some pretty rough events included on that list. But I left what might have been the worst one off because I wanted to show you in a little more detail. Along with the iridium in the Kpg boundary, we see a molecular burn marker called polycyclic aromatic hydrocarbons. This is all over the world. And these PAHs, as they are called, can form during combustion. The source is still kind of debated, but one of the most likely explanations is widespread forest fires. Now, how do you get widespread forest fires after an asteroid impact? Well, if you've seen a meteor in the sky or maybe a meteor shower, you've seen the effect of little sand grain-sized particles entering Earth's atmosphere. The friction between gas molecules and the particle heats it up, cause it to burn up. Back in 2013, there was a rather dramatic example of this. A much larger object, about 20 meters in diameter, entered the atmosphere over the Russian city of Chelyabinsk. It exploded before it could reach the surface. Eyewitnesses saw the light from this explosion up to 100 kilometers away. Some eyewitnesses also reported intense heat as a result of this airburst, explosion of a meteor high in the air. Now we can talk about the accuracy of eyewitness testimony another day. But that simulation from NASA of what a 20-meter wide asteroid may encounter moving through the atmosphere shows a lot of energy does get released. So we got a much larger asteroid, hits Chicxulub, hits the surface, causes a shower of ejecta, rocks from the surface of the Earth that are thrown into space. Some of them come right back down to the surface right away. Others are thrown high into space, almost into orbit around the Earth. They're going to come raining back down to the planet over hours, maybe days. Now, as each of these larger chunk of rock enters the atmosphere, it's going to cause more heating. And in the immediate aftermath of the collision, there may have been enough ejecta re-entering the atmosphere that the entire atmosphere of Earth was heated, maybe hundreds, maybe over 1,000 degrees. It's called a heat pulse or an infrared pulse, and that would have either made conditions more ripe for wildfires to ignite, or for some of the larger pieces of ejecta that came through the atmosphere, the very hot air may have just allowed the ejecta, once it hit the Earth, to ignite the wildfires directly. Another way the trajectories of this ejecta would have worked, a lot of it would have fallen close to the impact site, but much of it would have circled around the Earth and ended up on the antipode point, the point on Earth opposite the impact. And as Earth rotated under the stream of re-entering debris, the point on the surface of the Earth that would have been suffering from these impacts would have shifted. So you get the superheated atmosphere all around the planet, re-entering debris all over the planet. You're going to get global wildfires. The release of ash and soot from these wildfires helped darken the atmosphere, reflected sunlight back into space. You're going to cut off photosynthesis on the Earth. You knock out the base of the food chain, and that's really what does the dinosaurs in. But it actually gets a little bit worse than this. If it could get worse, than millions of pieces of impact ejecta re-entering the atmosphere and superheating the atmosphere. Core samples drilled into the crater itself found that the chemistry of the rocks under the Yucatan Peninsula may have been part of the problem. This was a shallow seafloor at that time. The rocks were rich in gypsum. So when these rocks were vaporized, large amounts of sulfur was released into the atmosphere. Previous core drilling samples also revealed that there may have been oil-bearing rocks in this region. Maybe it was just crude oil, could have been coal, could have been oil shales here. And if those were tapped into by the impact, perhaps some of those fossil fuels burned following the asteroid impact as well. either way, significant burning and heat trapping gases, aerosols, all of this stuff released into the atmosphere at the same time. The thing is, these teams estimate that only about 13% of the Earth's surface has the right chemistry to release either the sulfur or to have these hydrocarbons burning shortly after the impact. So if the asteroid had struck a slightly different location, maybe if it had arrived as little as 30 seconds earlier or later, it could have hit deeper ocean water, would not have vaporized these rocks. The outcome could have been very different. It's still big enough to cause regional destruction, but perhaps it would not have been a global catastrophe like we see if the impact site had been just a little bit different. We could be looking at a very different history of life on Earth. But the silver lining is that the same core samples show just how devastating the impact site was for the dinosaurs and many other forms of life. The impact also created new environments for life to take hold. An extensive hydrothermal system existed just after the impact because of the impact. And we know life returned to this region very quickly. Geologic timescales, we're talking tens of thousands of years, pretty impressive rebound. And then, of course, with the non-avian dinosaurs gone, mammals able to take over, and here we are. So despite the obvious threat, the dinosaurs had two things working against them. Again, the asteroid hitting just the right place, and if crude oil was to blame, the existence of life on the planet was also part of the extinction of the dinosaurs, which is kind of a strange circular bit of reasoning, but it could be the truth. So we should keep an eye on the skies for future events like this. Maybe we need just the right mix of these ingredients, an impact of just the right size in just the right place. So that means it's extremely unlikely that something like that is going to happen again this year or next year. And like I said, we don't know of any impacts the next couple hundred years. But we're talking about astronomical scales here, huge numbers. We've got billions of years, millions of asteroids. It's kind of like playing the lottery. It's extremely unlikely that any of us will win a single lottery drawing. But if enough of us buy tickets to enough lottery drawings, chances get a little bit better that somebody somewhere will match all of the numbers. So as you watch here, the 2,000 or so potentially hazardous asteroids that we currently know about, you can see their motions relative to the Earth. We need to be prepared for another unlucky lottery win for our planet. How can we be prepared for things like this? Well, we need to keep an eye out for these asteroids. We need to find the asteroids that we don't know about just yet. Back in 1998, Congress charged NASA with finding 90% of the near-Earth objects 1 kilometer or larger within 10 years. They did a pretty good job. They finished that search around 2010. Now they're looking to find about 90% of the near-Earth objects that fall into that potentially hazardous category, 140 meters or larger. A little behind on that goal. We're supposed to finish it last year. It looks like about 2/3 of those asteroids are still missing from our catalogs. Doesn't mean we're not doing our best. This chart shows the discovery rate for asteroids for the last couple of decades. It starts in 1995. You can see the uptick in discoveries in 1998 when there are dedicated near-Earth asteroid searches that get kicked off. The one shown in green happens to be the Catalina Sky Survey based in Arizona. They had a record year last year, as did astronomers worldwide, who found more near-Earth asteroids last year than any other year. But we're still missing a lot. We can expect these discoveries to pick up even more in coming years. NASA just approved a new space-based mission, space telescope called the NearEarth object surveyor is going to help us find as many of these near-Earth asteroids as we can. Let's see what this rate of discovery actually looks like. Last year was a record year. So let's look at the last year of asteroid discoveries. Now, I'm not going to go by calendar year. We're going to look from last June to just a couple of weeks ago. All right, so we've established that asteroids exist. We've established that large impacts can cause widespread destruction, and we're trying to find as many as we can. The next question might be, will we ever find all of the near-Earth asteroids? I can simply tell you no, but it might be better to ask, why not? Where do near-Earth asteroids even come from? If most of the asteroids are in the main asteroid belt, why is there even this group of asteroids that we need to worry about? So let's take a look at where near-Earth asteroids come from. Why do they exist? Well, it has to do with the orbits of asteroids in the main asteroid belt. I'm going to add to the map here a typical set of orbits for asteroids out in the main asteroid belt between Mars and Jupiter. It's a few thousand orbits, and together we can see that well, some of the orbits are tilted at different angles. We call that inclination. Many of them are very eccentric. They're oval-shaped instead of circular. We call that eccentricity. Now together, when we look at all of these factors, the orbits look kind of random. But there are some patterns here. If we get rid of the eccentricities and the inclinations, we reduce the orbits to circles that show the asteroids' average distances from the sun. And right away, some details jump out at me. There's some gaps in the asteroid belt. These are called the Kirkwood gaps, after the astronomer that identified them. And they exist because asteroids spend a lot of time at these distances from the sun, end up in a special gravitational relationship with Jupiter called a resonance. In a resonance, the asteroid and Jupiter are both going to complete some whole number of orbits in a given amount of time. Like for one of these, the asteroid will complete 2 orbits around the sun for every single orbit of Jupiter. You can have a 2 to 3 resonance, 3 to 1, 5 to 2. But the point is, when there are these repeating patterns, the asteroids are going to get repeatedly nudged by Jupiter, and Jupiter can push them into near-Earth space. You know, there are sometimes memes out there that talk about Jupiter being kind of our protector in the solar system. It sweeps up asteroids so they can't hit the Earth. In truth, its action is probably kind of neutral. It can pull in asteroids and comets so they don't enter near-Earth space. But Jupiter is also responsible for the near-Earth asteroid population because these resonances in the asteroid belt. So we need to keep an eye on not just the near-Earth asteroids. We need to understand asteroids all throughout the solar system, because some of those farther away could become near-Earth asteroids in the future. Now, we can certainly study them from the Earth. It's a great way to do it. But I think a more interesting way to get to know an asteroid is to send a spacecraft out to it to see it up close. And out of the 1.1 million objects that we know of out there, we've seen about a dozen up close with spacecraft. Out of those dozen, 4 of them are currently in the potentially hazardous asteroid group. So there are a lot of potential hazards out there, but we haven't seen that many of them up close. It's important to really categorize these asteroids because, well, a loose collection of rocks is not as dangerous as one solid chunk of dense rock. And in some cases, sending a spacecraft out there to study the asteroid is the only way to find out what kind of threat it really poses. Now, we can expect this list to grow in the coming years. There's a spacecraft out there right now called Hayabusa 2 that just returned a sample from one of these potentially hazardous asteroids called Ryugu, and it's now on an extended mission to fly by a couple more near-Earth asteroids. Later this year, NASA is planning to launch the Artemis 1 mission, and there'll be a hitchhiker on board called the Near-Earth Asteroid Scout mission, and it's going to fly by another small rock. And there's a spacecraft out there right now that has shown us more about one of these potentially hazardous asteroids than perhaps any other mission in history. It's one of my favorites, so let's take a look. The spacecraft is called OSIRIS-REx, which is a rather complicated acronym that I'm not going to get into today because the show's only an hour long. Now, it's been out here for a couple of years studying an asteroid named Bennu. It arrived at Bennu in late 2018, and it went into orbit around the asteroid, setting a couple of records along the way. Bennu became the smallest object to be orbited by a spacecraft. OSIRIS-REx set a record for the lowest altitude orbit around any object in the solar system, and it showed us a lot about what this asteroid was like. Let's go take a look at Bennu itself. Bennu is about 500 meters in diameter, so it's about as tall as, say, the Empire State Building. Well, it's one that actually is going to pass pretty close to the Earth in about 130 years. Not going to impact as far as we know, but it is one of the most dangerous asteroids we know of. It's big enough to cause some damage, and it gets very close to our planet. So that's why OSIRIS-REx was sent here to study it in detail. Thanks to OSIRIS-REx, we have a better global map of Bennu than we have of any world in the solar system. That includes the Earth. Now, because Bennu is pretty big, it's just not a lot of ground to map. We have the entire surface of Bennu mapped down to sub-meter resolution, and we can't say that for the Earth. There are parts of the ocean floor that we haven't mapped at this level of detail. So that's pretty impressive by itself. OSIRIS-REx, as we see its trajectory drawn in red here on the screen, it also measured the elemental composition of the rocks on Bennu. It found that many of the rocks have water-bearing minerals in them. So Bennu kind of adds to the story, perhaps, of how the Earth got its liquid water. There's long been speculation that maybe asteroids could have delivered some of the water that we enjoy here on Earth. But this show is all about impacts. So let's talk about the role that impacts play on Bennu. Bennu itself is an example of what we call a rubble pile asteroid. In these real images from the spacecraft, we see that there are just pieces of rubble all over the place. It looks like Bennu is boulders all the way down. So Bennu is probably a collection of smaller pieces of debris that were formed in a catastrophic disruptive impact on a no longer extant parent body. Also, on the surface of Bennu, we see some brighter colored boulders that have compositions matching that of another large asteroid, Vesta. Vesta is the second largest object in the asteroid belt, and the fact that some of its debris is on the surface of Bennu is a good reminder that Vesta has suffered some nearly catastrophic collisions. Debris from Vesta is spread across the solar system. There's a whole family of asteroids we think were born from these giant collisions on Vesta. And some of the meteorites we collect here on Earth, they match the composition of Vesta too. So little bits of this asteroid are all over the place. Little bits of Bennu could be all over the place too. OSIRIS-REx witnessed so-called particle ejection events, where little bits of rock were flung off of Bennu's surface. Now, there's some chance that micrometeoroid impacts are to blame here, but a more likely explanation is kind of a throwback to something I mentioned about the moon. On these airless bodies, you get wild swings in temperature, and Bennu rotates once every 4 hours or so. So every 4 hours, the boulders on Bennu's surface, a lot of B words here, of the boulders, they get warmed up for a couple of hours to very high temperatures. They cool down over the next 2 hours to very cold temperatures. These thermal cycles cause the rocks to expand and contract. Eventually, the stress is going to cause the boulders to break. And the microgravity environment of Bennu's surface, the little shards are created when a boulder fractures. They can be ejected into space, sometimes into orbit around Bennu for a short time. Sometimes they escape into the solar system. So there could be little bits of Bennu debris all over the place. Maybe some of the meteors we see in our sky from time to time actually come from Bennu also. At least one thing we're going to see in Earth's atmosphere is also going to come from Bennu, because the ultimate goal of OSIRIS-REx was to descend to the surface of the asteroid and collect a sample. So in these images from October 20th of last year, we see the sampling arm on the spacecraft. It makes contact with Bennu. The rocks turn out to be fairly brittle, so descended into the surface a short distance. Then it fires a puff of nitrogen gas that helps churn up all the material that you see there. And I've sped up this video about 3 times faster than it was in reality. The round device you saw at the end of the sampling arm, that was kind of like an air filter. So it let the gas out. It trapped the rocks. It's now stowed on the spacecraft. And OSIRIS-REx is on the way back to Earth with, we think, a fairly substantial sample of asteroid material. It'll be dropped off when OSIRIS-REx flies by Earth in September of 2023. It'll enter Earth's atmosphere, land in Utah. We'll have a little bit of a potentially hazardous asteroid right here on Earth, ready for rigorous scientific study. It's a bit safer than waiting for Bennu to deliver itself to the Earth. So we learn a lot about a potentially hazardous asteroid that way. Another important thing to know is, what do we do if we do find one that's going to hit the Earth? Well, there's another mission that is going to give us some clues. Launching later this year, NASA's Double Asteroid Redirection Test, or DART, is going to head towards a near-Earth asteroid called Didymos. It is a double asteroid, as the mission's name suggests. It's got a little moon called Dimorphos. Now, this video, I know, has a lot of fast motion. It's almost like it's designed not to work in a streaming environment like this, but the website will be posted at the end of the video, so you can take a closer look if you'd like. Long story short, DART is going to head out to the Didymos system. It's going to target the small moon, Dimorphos. It's got a little CubeSat on board with cameras, so it can image the system. Then the DART spacecraft is going to autonomously zero in on the moon. It's going to run into the moon on purpose. And the goal here is to see if a technique called a kinetic impactor could redirect a near-Earth asteroid if we found one on an impact course with the Earth. We'll be able to analyze the orbit of the moon from the Earth after the DART impact. A few years later, a European mission called Hera is also going to journey to the Didymos system and be able to analyze the moon and image the impact crater in detail. It's going to teach us a lot about how we might defend our planet in the future. And then we've got other asteroid missions coming up. We're going to visit some more near-Earth asteroids. We're going to send some new spacecraft to the main asteroid belt, learn about some unique populations out there. If you want to learn more, check out the Lucy mission launching later this year, the Psyche mission launching next year. I can get more into that in the question session if we'd like. But before I wrap up, I know that's a lot of asteroid information. I could probably talk about it all day. I want to kind of sum things up in this way. Obviously, asteroids are important to, our existence here on Earth, and they may be able to influence our future as well. And since this is lunch break science, I kind of want to weigh the importance of asteroids against what I'm going to call the lunchbox test. You go out, you buy a dinosaur lunchbox, you can find all kinds of variety. Maybe not all of them are super scientifically accurate. There's a pretty good chance you can find a lunchbox with your favorite dinosaur on it. Now, as for asteroids, space lunchboxes, man, some of the real ones for sale out there, not super accurate at all. Even the ones that try their best leave out a lot of the smaller worlds in the solar system. That one in front there, it's at least got the asteroid belt, but no mention of near-Earth asteroids. And those are the ones that we really need to know about. If you need kind of a take-home image, something to keep in mind, to remember just how important these near-Earth asteroids are, here's a little three-dimensional adaptation of a recent Planetary Society infographic. I've mentioned a couple of times that the asteroids don't need to be terribly large to cause citywide destruction here on Earth, about 20 meters in diameter. So here's a collection of all of the 20-meter and larger asteroids that we know of that have approached within about 250,000 miles of the Earth, inside the orbit of the Moon. Works out to being about 250 of these asteroids. That's if we just confine our view here to the last 100 years of close approaches and the next 200 years of predicted close approaches. The ones in white have already happened. The red dots show predicted close approaches by these asteroids capable of destroying a city. And it's kind of a tangled web here. So it's a good reminder to keep an eye on the asteroids. Also remember the number 0, though. No known impacts in the next 200 years. But something we definitely need to keep an eye on. And with that whirlwind tour of asteroids in the solar system and the effects of impacts, I can open myself up to questions for the last 10 minutes or so.
Okay, Justin, I just wanted to start off with asking, so what are some of the difficulties besides just space is a big place? What are some of the difficulties in spotting these asteroids?
So one of the big challenges is that, well, of course, asteroids don't emit any light of their own. So we have to rely on reflected sunlight. And many of the asteroids are very dark in color. So they absorb most of the light that hits them. They don't reflect it. So we also would benefit from using non-visible forms of radiation. Infrared light is a great way to find asteroids, but most infrared light doesn't pass through Earth's atmosphere. So you really need space-based telescopes to see it. That's part of the motivation for that new telescope I mentioned once, the NearEarth Object Surveyor. It'll be an infrared telescope that will keep an eye out for these dangerous asteroids.
Does NASA monitor asteroids when it's planning missions like Mission to Mars, or when it's looking at the ISS or that kind of thing?
Yeah, definitely. It's an important thing for them to fund. It's not the largest part of their budget, but what they do primarily is they provide money to groups that are operating these dedicated searches. There are a few of them. I know I mentioned the Catalina Sky Survey by name. It's actually operated by the University of Arizona. It's telescopes in Arizona. Just watch the sky every night looking for asteroids. But you got to pay the people that work at the telescopes, maintain the equipment, analyze the data. And so it ends up being funding from NASA that keeps searches like this going. And then there'll also be the funder for the space mission, the NearEarth Object Surveyor telescope. It'll be NASA funded. Also operated by, coincidentally, the University of Arizona in this case. But again, you need to pay the engineers that'll design it, build the rocket that'll launch it. So that funding is going to come from NASA. They're ultimately responsible for the mission, but it'll be operated by essentially contractors.
Can you kind of touch on the difference between like an asteroid and a comet, and what kind of risks are posed by comets?
Yeah, the big difference between asteroids and comets is that asteroids are more rocky and they spend more time in the inner solar system. Comets are usually farther from the sun. They've got more ice. And that's also going to mean that comets generally are less dense. So that means that if a comet hits us directly, it's less dense. There's less mass there for a comet of a given size. So it's more likely to burn up or break up in the atmosphere. It can also be pulled apart just by the gravity of the Earth as it approaches. We saw it pretty dramatically in the 90s with comet Shoemaker-Levy 9 as it approached Jupiter. Jupiter pulled it apart into a long string of smaller objects. Comets can get pulled apart. But that does mean you end up with more impactors, and the fallout from Chicxulub, that was more impactors. It's not necessarily a good thing, but because of the lower density, going to cause, on average, less damage.
Can you talk about the history of asteroids being discovered by astronomers?
Oh, sure. So it dates all the way back to New Year's Day, so it makes it easy to remember, 1801. That's when the first object in the asteroid was spotted. I'd love to tell the whole story, but actually it was featured in one of our live astronomy shows. It's now archived on Facebook and YouTube. Would have been all the way back last June. I probably did the whole story. But astronomers thought that there was actually another planet in the solar system between Mars and Jupiter. So a team of astronomers was getting organized to search that region, looking for this other planet. They called themselves the Celestial Police, which is kind of a funny name. And an astronomer, Giuseppe Piazzi, is going to be part of the Celestial Police. Before he received an invitation to join this search for a new planet, he spotted what is now called Ceres, just while cataloging stars in the constellation Taurus. I know there's a little bit of debate early on whether we should call this a planet or not. It's so small, looked more like a star in a telescope. That's how it ended up with the name asteroid. Asteroid means star-like. So Ceres, we found that. The Celestial Police continued their quest for this new planet. Never found a new planet, but they found a handful of additional asteroids. And then astronomers just kept finding them. It was just a few dozen at first, then hundreds. And it really took off in the 80s and 90s as digital detectors, CCDs, like we have in our digital cameras and our phones today. As astronomers started using those in their observations, that's when they really started to find thousands and hundreds of thousands of these worlds. As recently as the 1970s, we only knew of a few thousand asteroids in the whole solar system. So that's really kind of a recent phenomenon that we know of this huge number.
Okay, Justin, can you talk real quick about how asteroids are formed?
Oh, how are they formed? Well, that story really goes all the way back to the beginning of the solar system. The planets, their moons, asteroids, comets, they form from the material left over from the formation of the sun. You get a disk of material, gases, little dust particles. One of the still kind of open questions is how you get from dust particles to larger objects. We got a big hint a couple of years ago when the New Horizons spacecraft flew by an object way out beyond Neptune, out in the Kuiper Belt, an object now called Arrokoth. The more distant minor planets we think have been changed less over the history of the solar system. They formed to the size they are today. They kind of got frozen in time, so they're like fossils for the solar system. And what we saw in Arrokoth suggests that you get pebbles that form kind of like dust bunnies, and those pebbles start sticking together, and you get up to about a kilometer or 0.6 of a mile in diameter. And then you have boulders of that size, or I guess minor planets of that size. That's pretty big. That's kind of a characteristic size for objects in the early solar system. And then, of course, those objects are going to start colliding with each other. If they collide at a low enough speed, they can stick and grow larger and larger. So you get up to these dwarf planet sizes, like Ceres in the asteroid belt, like 950 kilometers in diameter or so. But sometimes the collisions are faster. So instead of sticking together, they disrupt each other. That's how you get the millions of pieces of debris. It's a long history of collisions and disruptions.
All right, so we are going to have to bring it to a close today. Looks like just about out of time. Thank you all for joining us today, and thank you to Mr. Justin Bartel for helping us discover more about our world. You can normally find Justin in the Dome, so if you stop by the museum, definitely do catch one of our live astronomy shows. Please join us next week on Wednesday, June 30th at noon for a brief introduction to the physics of baseball, presented by Dr. Patrick Woodworth, Assistant Professor of Physics at Virginia Commonwealth University. You can register for next week's talk at smv.org. Each talk is free to attend and is open to the first 300 registrants. Thank you again for joining us today. Until next week, stay safe and stay curious.